All right, accuracy and precision and percent error. So, accuracy refers to how close a measured value is to the accepted value. So the measured value is called the experimental, or the one you get in the lab. You obtained by measuring it through the lab tools. The accepted value is going to be one that you will find in a textbook, or it'll be on tables. These values have already been found and are known, and you're going to compare how close you get to them. Now, poor accuracy results from procedural or equipment flaws. Like if you're way off from the target value, that's probably because your equipment's not working, or maybe you didn't do something, you didn't follow the correct procedure in the lab. Let's talk about precision. Precision is how close a series of measurements are to one another. Poor precision results from poor technique. So say you're measuring the mass of a substance and or the volume of a certain substance, but you're not really paying attention to your graduated cylinder very well, and you're just kind of like rounding it to the next line or whatever. That's where we're talking about poor technique. You need to get down eye level with the meniscus and make sure that you're estimating that, last digit very carefully. That would help prevent poor precision, where you're getting data points that are all over the place. Okay? Now let's look at the targets. And yeah, you can draw in the arrows on the targets. So in this particular case, here is our target, and the arrows are kind of scattered all over the place, not hitting the target in the center. What would we say about the accuracy here? Poor accuracy, or very low accuracy. And they're also scattered all over the place. Are we hitting the same part of the target?
No.
No. So what happens here for the precision? Poor precision, or low precision. Now here's an actual data set that would show you something that has poor accuracy and poor precision. You see the actual value here. You see these, okay? Even if you average them, you're still not going to get anything close to that. And they're not even close to one another. 0.97, 3.92, they're all over the place. So this particular data set, if you had to comment on it, you would say has poor or low accuracy, poor or low precision. Now looking at the next target here. What would we say about this target? Poor accuracy, because we're not hitting the center, definitely. But are we at least hitting the same place each time?
Yeah.
So same spot means the precision is high, or you've got really good precision here, because you keep hitting that same spot. A data set that looks like this, where you have poor accuracy but high precision, shown over here, as you can see, the actual value being around 2. These measured values are more around 1, but they're very close to one another. So this data set is precise, but it doesn't hit the accepted or actual value, so it would be poor accuracy. And the last one here, where our arrows are all hitting the center target, as you can see. So what would we say about this one? High accuracy, high precision. A data set that would look like having high accuracy and high precision. Here is our actual value, of course, and you see all of the measured values are also around 2. So they're hitting the target value and they are very close to one another. So high accuracy, high precision. Now we're going to look at problem 1. Take a moment to read it and comment on the accuracy and the precision. Okay, so looking here, what would we say about the accuracy of this presented data? Poor, because here you see your different data, 4.5, 4.4, 4.6, not very close to the actual. So we would say poor accuracy. Good. Now, commenting here on our data set, these 4.4 and 4.5 and 4.6, what would we say about the precision? It has high precision. Very good. That is exactly right. Good. Now let's look at this one. Comment on the accuracy and precision of this student. Real quick. What would we say about this? High accuracy. Good. It's definitely close to the target value. But what would we say about the precision? Low. So you could say that's a good question because it only has the one data point. It's not really a data set. So yeah, I would say the precision is low. Or because it doesn't really have a data set, like there isn't precision at all to record here. You must have comparable measurements to be evaluating whether or not you have the precision. One data point isn't going to do it. You need to have, especially when we're doing, lab stuff, we usually do a couple of trials. So you do have at least 3 data points to go off of. Very good. I'm glad to see that you guys saw that as sort of a trick in there. All right, theoretical and experimental to find percent error. The theoretical value is the accepted value. And where are we going to find these accepted values? In a textbook, on tables online, out of these, chemistry, physics, indexes, or whatever that have all of the accepted values. That's where you would find them. And in our labs, I would tell you, I would give you the accepted value in the lab paper to go with. You'll have that to compare with. The experimental value is what you measure in your lab experiment. So you're actual measuring your data that you obtain while working in the lab. Oops. Thought there was more on that side. Sorry. So we use these terms, theoretical, experimental, for our percent error equation. Comparison of the experimental results to the actual or correct value. A low percentage is a good sign because that means you're not off by very much. So it's always the theoretical or actual or accepted, whatever you want to call it, minus the experimental, which is the data you get in your lab, over the theoretical times 100. What you should notice specifically is these bars. That is absolute value. An absolute value is telling you what? What does that mean? It's always what? Positive, because absolute value is actually a measure of distance. By how far off you are. We don't really care the direction. We just want to know how far off you are. Are you off by 2%? Are you off by 50%? Like how far off you are. It doesn't matter which direction. So if you do get a negative value on top, you need to make it positive. You can never, ever, ever have a negative percent error. That would not be okay. You might lose like a 0.5 on that or something if you put a negative percent error. All right, how far off are you from the target value? It's a measure of distance. let's look at an example problem. Here we have the mass of an apple is 150 grams. A student massed the apple and recorded it as 152 grams. Calculate the student's percent error. The only way to get these problems incorrect is if you identify the wrong one as theoretical and the wrong one as experimental. You might divide by the wrong number in that case. So always check to make sure you know you're identifying which number is the theoretical, which one is the experimental. So the 150, which one is that one?
Theoretical.
That is your theoretical, good. And the 152 is the experimental that the student measured in the lab. So all you have to do is set it up, show your work. So 150 minus 152, absolute value, over 150 times 100. Now, technically we would do the subtraction, sig figs, and then divide. I don't want you to do that because then you're going to get really like only one or two sig figs each time and it's going to not give you a very good percent. So since all of these, this number has 3, this number has 2, we're just going to go with 2 here. So just use the division rule here. Don't pay attention to the subtraction, just use the division rule. So if we calculate that, what should you get? You should have gotten down here, you can see 1.333 repeating, and it might have been a negative in there, so remember to make that positive. So I'm going to round it to 2 digits because we don't really want it to just be 1%. We want a little bit more detail there. So that's that practice problem. Let's go back up to problem 1 and use that data now to practice percent error. There is one little added extra step to this one. Does anybody know what it might, or guess what it might possibly be? Yes?
You have to add the experimental value.
Yes, you would add them, but really to do what?
You have to have the average of the,
We need one data point to represent the whole set, so yes, we would want to do an average, exactly right. So for that one, you have to average the data set first, so that you're only putting in one number for the experimental value. Exactly right. So do an average first, then set it up. Okay, so we take these 4.5, 4.4 plus 4.6, and we divide that by 3, so we get 4.5. This is now our experimental value. We can plug it into the equation now, because our target value, 6.2 minus 4.5, absolute value divided by the 6.2 times 100. And this one should be a much larger percent than the other one. What did you get? 27%, very good. Since these both have 2, I'm just gonna say go with the division rule and we're gonna say it has 2. All right? 27%. Your calculator answer would have been like 0.4 and then other things in there. So there's that. One more practice problem. You have 2 students here that collected quantitative data for their experiment. Calculate the percent error for each and circle the student who has the more successful experiment.
That means like the lower error.
We want the lower error, correct, exactly right. All right, I'm going to set mine up as well here. Student 1. right, what did we get for student 1?
1.45.
1.45%, very good, that sounds right. And student 2, 2.71%, exactly right. So which one better, came out more successful? Student 1, check. Had the lower percent error, very good.